Hi, this is Discrete Math, section 5.5, Kruskal's minimum spanning tree and also spanning trees. What we want to be able to do is two things. We want to be able to complete a spanning tree and then also find a minimum spanning tree using Kruskal's algorithm. So definition, what is a spanning tree? Spanning tree of a connected graph is a tree that is a subgraph of G and contains every vertex of G. So in other words, you're just bringing in every vertex into the system. So it might be like you're stringing out telephone lines. You just want to make sure that each vertex is included in this system, but you don't need multiple connections to one vertex. Then a minimum spanning tree is very similar to our cheapest link algorithm that we did before, but we want to find a spanning tree that has the least length or weight, and that is not dependent upon a starting point, ending point. All right. So the first thing we want to do is try to just make a spanning tree. This is the algorithm, breadth first algorithm. So we're going to pick a point S, label it 0, label all vertices that are adjacent to S and label them with a 1, connect all 1s and the 0s with an edge, label adjacent vertices to 1 with a 2, connect 1 with 2, and continue until all vertices are labeled. So we're going to start that off with this one right here, and then I'll talk about Kruskal's here in a second. So with this graph, we're going to start at A, and we're going to go ahead and call that my 0 point. So we're going to take all the vertices that are adjacent here to the zeros, and we're going to connect them with an edge. All right, now all we want to do is include all the vertices, so we're going to see how this goes. Now anything with a 1, the vertices that are adjacent to them, I'm going to call them a 2. So this would be a 2, 2. These are all adjacent to both these 1s. Then we connect them up. Okay, so that's what we have so far. Now what we want to do is continue this on. We're going to have some duplication, so you just have to make a choice which vertice you do want, because these will just come back. So this would be a 3, this would be a 3, and this would be a 3. I'm sorry, this was already a 2. So what happens with both of these 3s, you just figure out a way to connect them in. It's just creating a tree, spanning tree, so we just choose to do that one there and possibly that one there. I could have easily done this one instead of this one, but we don't want to include extra edges if we don't need to. Now this one right here would be my 4, and so now I have a spanning tree. So this spanning tree here brings all of the vertices into the network, but you don't make a circuit or anything like that, but you just want to bring all the vertices in and make sure that they're connected somehow. So if I did phone lines and I wanted to include this J vertice into the phone lines, but I was starting over here, this would definitely include it. And then I don't have to do duplications in other areas. So that would just create a spanning tree. So this is using the breadth first algorithm to make a spanning tree. Now, if you look on the other side, we're going to try to make a minimum spanning tree. This is where it becomes very similar to the cheapest link. So for Kruskal's minimum spanning tree algorithm, to find the shortest connections, we're going to list the edges from shortest to longest. We're going to darken the first edge. Select the next edge on the list. If it does not form a cycle with darkened edges, darken it. Now the difference with this one is that you could have 3 edges to one vertex. And so that's what we just have to be careful with. That's different than the cheapest link method, and so don't confuse the two. And then for a graph with n vertices, continue until n minus 1 edges have been darkened. The vertices and the darkened edges are a minimum spanning tree for the graph. So you need to include all of them as we go. And this is not a greedy algorithm. This one actually does find the shortest connection between the vertices. And the difference a little bit with this and the cheapest link, well, I'll talk about it later in class. So I'm going to start off with these edges and write them in ascending order. So I'm going to start with 1.2, and I'm going to write that. I might have to just tick that off slightly just to know that I took care of it. Then I'm going to have a 1.8 and a 1.8. So I'm going to tick that off. And then the other one is here. And then I'm going to continue on doing this. You can go do this as well. So this is the listing that I have of all these out. I did this previously, so I just wrote them down. But this should be the order that I go ahead and deal with. So if I start with the 1.2, the 1.2 is this one all the way across. So that's my starting edge. Then I'm going to go to the 1.8. And remember, you do not make a circuit. I don't have that problem yet, but it will probably come up here in a second. Then I got a 1.9. So if I go to a 1.9, that'll be there. Then a 2.0. The hardest thing is finding these. Now if I look here, now I'm going to make a circuit with this 2.0. So I'm going to have to skip over the 2.0 and move on to the 2.1. So if I look at the 2.1, that does not make a circuit. Now the question is do I have all of the vertices incorporated? And the answer would be yes, and everything is connected as well. And so this last one made a connection so that we do have a network all together there. So I used the 1.2, 1.8, 1.8, 1.9. I had to skip this one, and then I did the 2.1. That was all I had to do. So you don't always have to write out all these values, but start from the lowest and finish with the greatest, or go part way and then until you had to keep on going. So this would be how you would do the minimum spanning tree for this network, and this is the shortest spanning tree that you need for this. This last one is one that is in your book, so why don't you go ahead and try this one yourself, and then you can go check the answer in the book and to see if you did do a minimum spanning tree. All right, so that's all I have. The homework is listed on the page, and that's what you're going to have to do for today. All right, thanks. Have a great day.